It's a challenging question, right? Because geologists are very focused on explaining processes using internal mechanisms to the planet. And that's because that's stuff you can go and actually measure. And it's also because it's within your discipline. So when you start proposing extraterrestrial processes affecting geology on the planet, you get quite a bit of pushback.
It was cool to hear somebody talk about how the oldest dates we have are essentially a hard stop sign because the Earth has been reformed, and when it's reformed, your clock's reset to some extent. And so maybe our timelines on how old this place are just as far back as we can see, not so much an absolute wall.
Yeah, and Chris Kirkland, who is a geologist at Curtin University, has a theory that develops this idea of, we can only see so far back, and when we look far back, we have to really start to get creative about mechanisms that explain what's actually happened. And so he's on the show to talk about geology and radiometric dating and all of the sort of the intricacies of being able to look into the deep past, but also because we're a show about theories, he's here to tell us about his theory of how it is that the earliest crust on Earth was formed. And it's not a solely Earth-based theory.
Yeah, so Dr. Kirkland noticed some interesting harmonic irregularities in the way that the crust changed periodically. And then he and his colleagues tried to correlate that to cosmic events, particularly the transit of the Earth through the galaxy, which is a really cool idea because it seems to be one of the first times in the relatively new science of geology, in a modern sense, that folks have begun considering non-planetary processes in the formation and evolution of the crust, the surface of the Earth.
So we think that you're really going to enjoy it. It is a stellar theory, actually technically interstellar
theory. For sure.
Interstellar for sure. And one thing that we just want to say before we go is thank you so much to everybody who supports us on Patreon. We could not do it without you. It is a pleasure to look to see that there are people who love the show and who support us in order for us to keep making it. If you have not joined our Patreon yet, it's at patreon.com/demystifysci. And you can sign up for as few as $3 a month. And it is absolutely so good for us when you do, because that means that we can keep making more and more of these episodes and keep doing cooler stuff.
Yeah, and our patrons have been hanging out once a week with us and really helping us guide how to make better and better podcasts and who we should be talking to. And it's like our feelers, it's our antenna. It helps us feel grounded to the realm of curious people like you who are listening. So come over, check it out, and enjoy this conversation with Dr. Chris Kirkland.
The scientific revolution starts now.
The Demystified Podcast.
Let us see in the dark.
What do you spend your days doing? Like, what is the typical day?
Yeah, the typical day for me is I get into work, see some students probably in the morning, some PhD students, and then go and try and find some time to play in a lab. And then, maybe crush some rocks, press some buttons on a mass spectrometer, and then in the afternoon, try and write some stuff. And if I'm really lucky, I get some field work during a couple of times during a month. So we go and look at some drill core, or if I'm very lucky, I get a chance to get out to some, take a 4-wheel drive and drive out into the bush, out back and sample some rocks. So that's the highlight.
Yeah, I have a vision of geologists as being very outdoorsy people. What were you going to say?
Yeah, I just want to hear about what happens when you start crushing these rocks up. Can you walk us from, well, first of all, why are you crushing all these rocks up? But yeah, let's figure out what happens to them exactly.
Yeah. Okay, so the first part is obviously like kind of field work and sampling, and that's critical. So if you collect the wrong rock, you're not going to tell the story that you want to tell or get the information that you want to get. But you get your lab, you take it back to the lab and start sawing it up with a rock saw. So that's just like literally like a bandsaw with diamond blade. You chop it up into little cubes, and then that gets crushed. So there's 2 ways of crushing stuff. The traditional way is just like in a jaw crusher, two big metal plates going back and forward, and they crush the rock into sand-sized material. But we have this cool device called the self-rag, and you put the blocks of rock into a bucket of water, and it discharges like a lightning bolt at the rocks, and they basically turn into sand instantly, but they fracture along the grain boundaries, so you don't damage your grains. So everyone makes a joke, like the lights in the building dim when you're setting it off, but it's not quite that. It's not quite like that. So you have your sand, and then you pass your sand into a flask filled with heavy liquid. So heavy liquid's liquid with a high density, and that allows light minerals to float, but heavy minerals to sink. So that's your first separation process, and we're interested in the dense minerals because they tend to contain uranium, and you tap that liquid off at the bottom. And then there's other separation procedures you can go through. So you can put it through like a slide that's got a magnet on it, and that will do a magnetic separation. And then it's a pair of tweezers in a Petri dish and pick individual grains.
I assume you said uranium because you're interested in dating these rocks.
Yeah.
And
is there any other reason to put lightning through rocks, or is it just for dating?
Well, other than it's very cool.
Okay. So it's a tight funnel towards dating.
Yeah.
So,
go ahead.
So you use this uranium to date the rocks.
Yeah, that's right.
Yeah. So this is a really, really foundational procedure for so much of geophysics.
You're absolutely right. Yeah.
Maybe
geophysics. Yeah.
Maybe you can just lay that out for us,
Sure,
in terms of we can actually imagine how these isochrons are generated and what's the process?
So it's sure. So it's, if you get your head around it, it's quite profound. So there's lots of different decay schemes, and there's a whole range of different decay schemes that can be used. And you mentioned dating something, and everyone naturally jumps to kind of carbon dating, but for geologists, looking at this idea of deep time, lots of things that are very far in the past. The uranium lead system is the gold standard. It's quite spectacular how well it works, and it works so well because there's 3 different decay schemes that you can use. So you're looking at uranium 238 uranium to 206 lead, 235 uranium to 207 lead, and then you're looking at a thorium to lead scheme. So you've got these 3 independent clocks. And the cool thing is that those clocks, when they agree, will give you a single age, but the clocks sometimes might not agree. And that's okay as well, because that tells you about other processes. It tells you that that clock isn't working perfectly, but there can be reasons why that clock isn't working perfectly.
That's critical. I want to come back to that, but just to clarify, every atom has something of a shelf life, it seems like. And so as they each fall apart, then they're going to fall apart at different rates, and we can triangulate the curves. I guess they're lines upon which these degenerate. But I guess they're curves, right? It's an exponential function. So
yeah, that's right. So it's a negative exponential function, which is a function of the kind of half-life. So because we know the half-life very well, the parent isotope is unstable, and over a certain period of time, it'll decay to a daughter. So if we can measure the daughter and the parent, assuming that there was no daughter present at the start, we can do a calculation that gives us an age. So because we got these multiple different clocks running at the same time with different parents and daughters, we get what's known as a Concordia age, and that's where where 2 of the systems are plotted against each other to see if they agree. So it's a little bit different from, you were mentioning a line, which is an isochron technique. We can do that as well, but that because the uranium lead system has got these inbuilt checks, we don't really use the isochron technique as much. So the isochron technique is where you're plotting the parent, the ratio, the amount of parent, if you like, against the amount of radioactive daughter. And if you've got different amounts of parent through time, you will develop a slope, and the higher the slope, the older the age.
Interesting. So you have to assume that none of these daughters made it into the sample, and then the other principal assumption, I guess, is that all of this parent came from the beginning of the rock.
And they're also has to be the assumption of the half-life of uranium, which is
Oh yeah, I forgot about that.
4.5 billion years, which doesn't seem like something that we've laboratorily deciphered, right?
Sure.
Yeah, that's an interesting one too. So can you unpack each of
they-
those for us? Yeah.
Yeah, sure. So we'll take if we take the idea that we're looking at the amount of parents, the amount of daughter. One of the critical aspects is that there's no daughter present at the start of our clock, right? Because if there's some daughter present at the start of our clock, our ratio is going to be messed up. So there's ways of correcting for that, but there's also a kind of an even simpler thing, which is we can use minerals that don't like to contain lead. So they have no lead in them when they grow. So any of the lead that accumulates in them is from the decay of uranium. And the kind of premier example of that is zircon. So that's a zirconium silicate. And it's really the timekeeper for a lot of geological processes. So these crystals contain tons of uranium, which is great because that's what produces our clock. And that uranium decays and produces lead, and that lead gets trapped in the crystal. But it's at time zero when the crystal formed, because it doesn't like to incorporate lead, there'll be no lead at the start. So one, we don't really need usually to make a correction, but if we do need to make a correction, there is mechanisms of figuring out how much of that what's known as common lead. So that's lead that isn't produced from the radioactive decay that we need to subtract out.
And you get that from the rocks that are found around it, or what, how do you understand the common lead?
Yeah, good question. So there's actually several different ways of doing that. One would be to measure a crystal that loves lead but doesn't like any uranium. So that's a good signature of the common lead. And that's one way of making that correction. The other way of doing it is a kind of an iterative approach. So you've got some kind of ballpark age that you believe the crystal is, and you can then refer to models that make a prediction for how much the isotopic signature of the common should be, and then you can compare that to the measured common.
What's that ballpark from? Just like from an isochron or something?
Yeah, so you can basically use the uncorrected data to say, hey, if this had no common lead in it, it should have this isotopic signature. I go and measure it. I've got a slightly different isotopic signature. Then I can work out how much common is in there to subtract. Like I said, these corrections in zircon are either you don't need to make them, they make no difference to the age, or usually very small. For other minerals, so other minerals such as apatite or titanite, they also contain uranium, but when they grow, they contain some lead. So those are the ones that we need to be more careful with and usually perform a correction on. So multiple different ways of carrying out a correction, typically involving measuring another. One way is to measure another crystal in the rock at the same that grew at the same time.
And then this uranium. So the uranium must be assumed to have arrived at the rock at the same time as everything else. Is that correct? Or when the rock was formed, I guess.
Yeah, so the classic thing geologists like to do is date igneous rocks. So that's a rock that's crystallizing from a magma. So yeah, when the crystal grows, it's assumed to trap uranium in its crystal structure.
And where does that fresh uranium come from?
Yeah, so that liquid will contain uranium. Now, where that originally was produced would be the mantle, but then through fractionation processes. So that's kind of a separation process. You have a liquid that's then going to be buoyant and rising. Uranium typically likes to go into the crust, and the mantle normally becomes more depleted in uranium. So things like granites are fantastic to date because they tend to crystallize zircon. They tend to crystallize these crystals that contain lots of uranium, whereas more iron and magnesium rich rocks, darker colored rocks like basalt tend to be much more difficult to date using this technique. So I don't like seeing this in my lab as much.
I guess I'm asking, like, so fresh uranium is one of I think it's the second biggest element. It's enormous, right? Where do you get completely stable fresh uranium that hasn't decayed at all?
Like, where is uranium? Is the question, where is uranium made?
Yeah.
And how does it, and where is the uranium made that ends up in the earth that then over time becomes incorporated into these crystals?
Like is that uranium getting made, is plutonium decaying into that uranium, or is it coming fresh from a supernova, or what's happening exactly?
Yeah, so I think the general idea is it's one of these nucleic basically produced through star formation processes.
And so it's basically the idea behind the technique is that as long as all of the uranium that is ever going to be on Earth is on Earth at the 0 point of Earth's formation, then you will have a consistent clock that you can go all the way back to the very beginning of Earth's time to be able to make these curves. But if you were, say, I don't know, say like a uranium meteorite, which I don't know if those exist or not, like hits the Earth, does it screw up your clock? Or say uranium's coming from the inside of the Earth?
Yeah, so it's just a decay, right? So it's just a change of the uranium to lead. So as long as that decay rate remains constant, and we know that decay rate because we're looking at the change of uranium to lead, then we should be good. So there's been a lot of uranium lead carried out on meteorites and even pre-solar grains. So the technique works for non-terrestrial material as well. But it's critically dependent on understanding the decay rates.
But do you assume that all of the uranium, all of the heavy uranium is from the starting point, because no fresh uranium can get into it, basically?
Well, I think that the point, if I'm understanding correctly, I think that what Dr. Kirkland's saying is that even if you add fresh uranium, it wouldn't change the date that you get out of the sample.
Yeah, pretty much. So like within the crystal itself, we assume that there is no loss or gain of uranium, but that you're hitting on a really important aspect, which is this test for these chemical processes that happen after the crystal forms. So our crystal forms and it'll capture uranium at growth, and that uranium will change to lead, and that's our clock. But if there is some loss or gain of uranium or loss or gain of lead, that will break our clock. But the neat thing about it is it won't break all the clocks the same. So some of the clocks will become more broken than others. So we can plot that up on a graph, and we get two really cool pieces of information. Then if we have multiple broken clocks, we can backtrack to when the clock wasn't broken, but we can also backtrack or forward track or recast to when the clock was broken. So we get these two pieces of information, which is really interesting. So we can get a formation age, but we can also get this age when the clocks became broken. And that typically is when fluids are passing through the rock. And that's, for geologists, a really interesting thing, because fluids carry metals, but fluids also can be what weakens a rock and causes faulting to happen. So when the clocks aren't broken, we call that concordant. And that's typically in a magmatic system when no other later fluids have passed through. So that's great. We're happy with that. But when the clock is broken, it's called discordant. And the critical thing there is that all the clocks don't break in the same way. So we can use these kind of like line fitting techniques to cast back and forward.
Something that I think would change the clock is a change in the rate of decay, right? And so, I've seen some stuff. There's, who's the guy at Stanford? Peter Sturrock? Do you want to tell the story? I don't remember it exactly, so you have to tell it.
There's just been several people. We wrote down. I mean, we were talking about a few of them this morning. There was a Purdue group that worked with Sturrock. There was just some evidence that the different solar cycles were affecting the radioactive decay in some experiments on Earth.
Yeah, so I've read a bit about this. I think that was quite controversial research, which is great, because I think another group basically weren't able to show that effect, and there was some discussion whether it was about the measurement process itself. As a geologist or a geochronologist, we use this uranium lead scheme to date rocks, but those same rocks can also be dated with Other isotope schemes, maybe not as precisely, but a good example is I'll come back to a granite, a nice granite benchtop, for example. It contains zircon. We can date that with uranium lead, but it probably also contains micas, and those micas you can probably date using rubidium strontium. So again, a completely different decay system, but they can frequently, when that's been done, and the ages will match or reflect the same process.
That makes sense. But if they were subject to the same pressures, then their decay schemes would be altered similarly, it seems like, as well.
You're thinking some kind, like if neutron bombardment from the sun would change the decay rate of everything equally, and so you would have basically either a stretching or a compressing of the dating scheme across that period of time?
Or you would just see, like, the method that Dr. Kirkland's describing is extremely internally consistent. That's the wonderful thing about radiometric dating. But the absolute date of it depends on this being a constant. And if the constant is due to interactions with cosmic matter,
that's kind of what I was saying.
Then the absolute date can shift, but the internals will still be consistent, is what I'm thinking. I have no reason to doubt it. I'm just thinking about whenever we have a model that we're fitting curves to, we have to think about like the underlying assumptions to it,
That's absolutely right. So the other thing as well is this technique works better, kind of paradoxically, works better the older in time you go, because you're right, you're going to have more of the daughter, so it's easier to measure. So younger stuff with this method is actually more challenging. But we can date to probably pretty young with this technique. But also, with this decay of uranium also produces helium. Through the decay of uranium to lead, you get helium released, but you also damage the crystal. So the crystal lattice will start to show damage marks, which is called fission tracks. So there is other techniques as well, which can be applied at the younger end, and they kind of would correspond or give us confidence that the decay rates are pretty well known. Yeah.
Oh, sorry, I didn't follow how that would tune to the decay rates.
Because I think that you get more helium tracks in a sample that has decayed more. So there's basically like a physical perturbation of the crystal structure. And so if you look at these decay rates and you get some kind of date, and then you look at the way that the crystal structure has been perturbed, which is thought to be from the production of helium, then you can say that if the crystal structure is correspondingly perturbed, it appears to correlate to the age that our radiometric dating is telling us. It's like a physical marker of crystal decay, which is weird.
Spot on. You explained that much better than I did, but that's exactly it. So you can imagine the guys in the lab that do this, they stare down their microscopes and look at these tracks, which literally are little tracks.
And they're like counting them?
And they count them. Yeah, they're counting them, yeah. And they have software to do this now, but that's kind of hardcore.
Is it atomic force microscopy? Is it electron microscopy? Like what level of detail?
No, literally just transmitted light microscopy.
It's that much.
Yeah, you can see them. So these grains are probably about the width of a human hair. By length 300 to 500 microns, but within them under a decent microscope, you can see the little tracks and count them.
See, that makes sense to me. Like, I have no doubt that it's internally consistent.
Yeah.
Like, it's telling you things that are older.
Yeah, you're asking a question, which is like, is the entire foundation of the discipline suspect? Because
No. I'm not being so severe.
But I think that it's worth considering the implications of the question, right? Because that is the implication of the question, which is like, can we trust the discipline? And it's
No. Not at all. I mean, the discipline's much larger than putting like 5 significant figures on the date of the universe or on the date of the solar system.
He's teaching an astrophysics class, and yesterday he was telling me that in the textbook they had the date of formation of the moon to 3 significant figures.
Yeah, it was. There's just like this. There's definitely an air of certainty about some of these. It's hard for us to even it's hard for me to explain to somebody how long ago 4.5 billion years was exactly. Like, it's an inconceivable amount of time.
Let alone 3.682 billion years
Yeah,
ago.
right. So, and we've updated our story about how the moon was formed significantly in the last 10 years. And these stories are just constantly changing. And that's what's so fascinating to me. It's just how at every single age throughout history, somebody's been standing there like, we know the certainty to 20 decimal places, and then it turns out like they didn't even have the right model, let alone the certainty of the calculation. So I'm always just kind of curious how these things might develop over time, and
So I guess where we can get to with this, because if we want to go to the kind of like the extreme younger end, because that's stuff that we can physically see, is then looking at dating archaeological artifacts or stuff within tough horizons. So that's like volcanic horizons. Volcanic horizons are great because they tend to grow magmatic crystals in the chamber that then gets exploded out. So you can date stuff that does have a historical record at the extreme young end.
Extreme young end, I feel better about than the extreme far end for some reason. I'll tell you, like, let me just explain really quickly why I feel so like curious about this.
Some background is in order.
Yeah, it needs to be said that like everything that we've ever dated has not been able to dig past 4.5 billion years ago. This includes all the meteors, all the planet surfaces that we can touch, anything, right? But this is really strange because they've started to find these interstellar objects impinging on our planet. And so if they've seen 3 of them in the last decade, the chances are there's been a lot more than 3 in the history of the Earth that have hit the Earth. And my question is like, I have a really hard time swallowing that everything in the local galaxy even is 4.5 billion years old also, which makes me like very suspicious of that number, because I'm just like, it doesn't make sense to me that things from outer space would be the same age as things here. And I'm kind of like, what assumption could be awry here? I don't know.
I'm not sure any assumptions are awry, but if you think about the physical processes on our planet constantly kind of resurfaces itself. So it's actually, if we go out into our back door, it's actually quite rare to find old rocks. So like for a geologist, those would be called Archean rocks. Never mind finding even older rocks. So like the oldest record that we have is detrital crystals. So those are crystals essentially from sand, right? And they're eroded out of older granites. And they're only like about 4.4 billion years old. I say only, and that there's only one place on the planet we can go to find those. And that's eroded bits of grains. In terms of the oldest physical rock, we need to go to Acasta in Canada, and that is just about 4 billion. Okay, so these older records typically come from meteorites and meteorite fragments that can be dated at 4.5. But the majority of rocks that we actually go out and look at are much, much, much younger. And the planet physically, resurfaces itself. So anything in the oceans will be subducted away, and that will be much younger, much, much younger. So the crust, or those solid cratons that kind of float, they're our older record of history, but even those are usually, some of the oldest of those are in Canada, the parts of the US, the Lewisian in Scotland, and in Australia. And those are probably only between 3 and 2.5 billion. And I say only because these are mind-bogglingly large numbers, billions of years. So the chance of actually finding something is, it's probably there. It's just eroded away.
I see. So you're like, there might be really, really old stuff, but it's just been gobbled up by the Earth since it was deposited.
Yeah.
And we just don't know. And so the conservative way of putting it is, hey, the planet itself is only 4.5 billion years old.
Yeah.
That's fascinating.
Yeah,
I appreciate
that would be what I'd say. Yes. So like, that's why Jack Hills is like a mecca for geologists, because you can go and find these little individual crystals that tell us about this early history of the planet. And you can look at these zircon grains, you get an age, but you can also look at the zircon grain and extract out more chemical information about what the early planet looked like.
But it's not necessarily the earliest planet. It's just the earliest that you have a shred from. I see.
Yeah.
Okay, that's somehow much more reassuring than than most people discuss it, you know?
Shiloh's going to stop waking from nightmares now. So you have settled you have settled something deeply important for the man.
That's good.
I want to know about, you said something interesting, which is that recent stuff is trickier. And so if you were to go to an active volcano and collect some stuff that had just come out, what kind of a spread of dates are you going to get?
Yeah, so this is actually at the tricky end of things, because our clock will only just have started, so it's actually really difficult to measure. And at that end, you're better off using different decay schemes, and there are much more appropriate decay schemes. So that's decay schemes that accumulate daughter faster, that you can use to date younger volcanic processes, which is kind of important because it helps us predict volcanic hazards and things like that. But in terms of zircon and uranium lead, when we get to young volcanoes, what we typically find is that while you have a magmatic component and a component that tells us about that eruption age, you also have components that are stuck in the chamber that have been growing and haven't come out yet. So you get it's never a neat individual age. It's usually an age, but other crystals that have been grown earlier in the system have also got thrown out at the same time. So young volcanoes are particularly challenging to work with, and that's why working with older stuff.
It sounds impossible. Is there like a density component to this too, where things are rising and falling in that column?
Yeah, exactly. That's we have crystal settling processes. And you have flow processes. So like you can actually go and look at some rocks and you can see, like what look like flow channels within them, but those are igneous flow channels, so magmatic flow channels. But so some crystals are settling, some crystals have grown earlier, and then some crystals are growing as the rock itself is solidifying. So as you start to get more and more zoomed in to the processes going on in a rock, it gets more and more complicated, but I think that's just the natural environment. So you can step back and you can say, oh, broadly, it's this age. But if you go and look at it in detail, you can see a whole variety of other processes. So some of those processes are the chamber itself getting recharged from more material coming from the mantle, and then the chamber growing, and then the chamber actually erupting. So I mentioned there's other decay schemes. So one of those decay schemes, or one of those processes that you would use to date really young grains would be uranium, thorium, helium. So rather than uranium to lead, you're looking at uranium and then the gaseous product helium. And helium can get trapped within the crystal structure. And there's a whole range of other assumptions around that, but it works much better for younger stuff.
And so it makes sense that you would have a different decay scheme for stuff that was younger, because I mean we kind of already know and accept that if you're going to be dating something that is relatively recent that was once alive, you're going to be using carbon and not this same uranium scheme. So it's like
the half-life is crazy, right? For uranium, it's very, very long.
I think 238 is 4 billion years. 4.5. I think it's 4.5.
Yeah. So how about that for serendipity? Right?
I'm sure it's just a coincidence. But okay, so at the very beginning, you were describing the fact that you take your box of rocks, you put lightning through it, and then you have sand, and you're filtering through your sand. Like you've sifted your sand, you've gotten your zircons, but you're going through with tweezers picking out zircons from a slide, right? And so you get like, how many zircon grains do you get per sample? Because you were in the email to Avi Loeb, you mentioned that it was like you need a fist-sized rock. So if you have a fist-sized rock, how many grains are you getting out of this?
Yes, I mean that's one of the things. So like the grad students will be like, "Oh, I've picked 20 grains. Is that enough?" And you're like, "Well, it depends on the question, right?" So if we've got a magmatic rock, like I keep coming back to granite because that's the easiest thing to work with. The granite, all the crystals will probably have grown at the same time. So 20 grains and 20 to 50 analyses might be enough for quite an accurate date, because they're all going to give the same number, or you hope they're going to give the same number. But if we're looking at what we call detrital samples, so that's trying to get a fingerprint of the age of what's in a sand, for example, to understand where our sands might have come from, to understand, the eroded history. So to understand something about rocks that don't currently exist in outcrop, you probably want thousands of grains. So that means quite a long time with a pair of
A
tweezers.
lot of grad
Coffee.
students. Yeah.
Yeah.
Oh, that sounds so painful. Okay, and so then when you've collected
Nightmares of grad school coming back to all of us.
How
Yeah.
long does this take? Like, how long is somebody picking rocks? What
Yeah,
for
okay.
1,000 grains?
That's a great question, because there's actually shortcuts, right? So when I was doing my PhD, we were there with tweezers. And it'd take maybe, if you were good, you could probably do one sample a day. But now we've got techniques where we can just take the heavy minerals, so that have fallen out in our separating funnel, and we can dump them all onto our double-sided sticky tape, and we cast it in epoxy resin, and we polish them to half grain thickness so we can see the internal structures. But we can take that straight away to a scanning electron microscope, which has some detectors that will characterize the individual grains. So we can have a whole range of different heavy minerals. And rather than having to hand pick them, we can just get the microscope to scan across the surface and go, well, highlight all my zircon blue. And then I'll go to we can talk about the next stage of the analysis with a map. So rather than having to do all the horrible hand picking, you can let a machine basically color code stuff for you. But we still do the hand picking, especially with grad students.
This is the kind of stuff that makes me realize that scientists, or at least some large number of scientists, will be obsolete in the next 50 years. Because if you don't need grad students to handpick the samples, what do you need grad students for? It's like people don't need children to run farms anymore. This is a discipline but that's a different conversation.
There is reasons to actually handpick, because when you handpick, you tend to pick the best crystal structures, and the best crystal structures, for if you're asking for a magmatic age, are probably the ones that are going to be most concordant. So remember back at the start, we said ones that the clocks would agree. So you can actually already make a prediction. So those grains that go black, in other words, the crystal lattice is damaged, are more likely to be the ones that have lost lead. And if you're trying to find a magmatic age, those are the ones that you probably wouldn't want to analyze. If you're interested in the whole history of the rock and telling something about, these overprinting fluids that might have come through, then you want an unbiased sample. So going the route of having a microscope to scan rather than a person picking is probably a better route.
Grad students have breathed a sigh of relief. You're not getting rid of them yet.
So you need a fist-sized chunk of this extra, what is it? What we call intergalactic rock in order to proceed and see how old it is. Why do you need a fist-sized piece of it? Yeah. Why so much?
Well, normally we deal with between 1 and 5 kilograms, and that will get us, tons and tons and tons of zircon, and able to replicate things. If we find an unusual result, we can repeat the whole process again. A fist size piece is that'll fit in your pocket, right? So that's an easy size bit.
Is it just that that's the only way is the only way you're going to get enough zircons? You need that much to find these little crystals, right?
Because most rocks don't have a ton of I remember reading something somewhere where it really kind of shifted the way that I understood geology, which is that not all rocks could be dated, because not all rocks have zircons. You have to have something that's derived from a relatively recent melt, or not even just melt event, because metamorphic rock wouldn't necessarily have zircons in it unless you have some kind of fracture flow event where they're deposited. The
zircons have to get made right at the beginning of the clock sometime.
Yeah, exactly. And the rocks that contain zircons that are made in the rock, I think, is largely granite.
Yeah, so that's right. So zircon tends to grow in what we call felsic rocks. So felsic is like a light colored rock, like granite. But it's not just granite. There's quite a large variety of rocks that will grow zircon. But when you get to the iron and magnesium rich end, so we call those mafic rocks. So those are things like basalt. You're entirely correct. Those are a nightmare to work on, because they will contain a few zircons if you crush a big enough sample. But those zircons tend not to have grown in that rock. They tend to be inherited and to have come from somewhere else. But that can actually be really interesting, because that can tell us about what the geology is at depth that the basalt might have come through. So people actually go and try and look for these really iron and magnesium rich rocks to tell us something about the deep geology, not necessarily about the crystals grown within it. The other cool thing is that
but that would that give you a true age of the rock then if you
no, absolutely not. But it would give you an age that would reflect somewhere else in the stratigraphy. So that's spot on. It wouldn't tell you anything about the age. Well, it would place a
constraint of some kind.
A constraint on the age
right.
of the basalt, but it wouldn't tell you about this specific age.
And I would assume that meteors are kind of similar to basalts, right?
They can be more intermediate in composition, so they don't necessarily. Yes, they tend to be towards the more iron and magnesium end, but it depends, right? There's a whole range of different meteors, right? So you can go various chondritic compositions. Some chondritic compositions can be felsic enough to grow zircon.
And so I want to. So we spent a lot of time in the Pacific Northwest, and the Pacific Northwest is the location of one of these like big basalt provinces, right? The Columbia River basalt group. There's there's places where there's a mile of basalt, right? So it's very much part of the central story. And I used to give tours out there, so I had to tell the story of the Columbia River basalts a lot. And something that I didn't really totally get was the journey of the basalts inside of the earth, because it comes out of some kind of volcanic dike or some kind of volcanic eruption. And my understanding was that it was just stuff from a mantle plume that made it to the surface and then came out. And so when you're saying that it's the history of the basalt, do you mean that what it's telling you is that the rock came kind of from closer to the center of the earth and as it passed all the way through the mantle? Or is it something that's being formed in a more shallow area and then surfacing? Is there a good sense of that? Because tomography maps are nuts. I look at tomography maps and it's basically like scrambled eggs.
Yeah, where are those zircons being made at? Down deep?
Yeah, so that's a really good question. So you can form zircon in a whole variety of different places. It tends to grow in rocks that are around 65% silica. So those are again quite felsic rocks. But on that basalt's pathway, it will pick up deeper bits of crust. So it'll assimilate those other bits of crust, and their zircon cargo will get absorbed and carried along with that basalt. That basalt itself, where it gets really fractionated, and sorry, that's a technical word, basically means once it splits enough in rare places where there is some water in the system as well, can grow zircon. So you can do stuff with basalts. It's not quite as doom and gloom as I'm portraying, but they're not easy to work with. But yeah, so like typically in extensional provinces or plume-related provinces, the ultimate source of the magma will be the mantle. And that mantle plume will rise because it's buoyant and it's losing its energy as it's rising. And it's equilibrating chemically, but also thermally with the surrounding rocks. And where it reaches the surface, it will become extrusive. So, large basalt flows, but possibly also, volcanic outpourings. And the importance of volcanics within the sequence is they give you a very direct time marker on the stratigraphy, because that's a horizon that could be dated, that you would have a specific age point for.
What about in the meteors? Are they thought to have formed at the same time as the meteor, these zircons? By what processes?
Yeah, so again, wide variety of different meteor fragments, but many meteorite fragments are assumed to be igneous rocks based on their petrology, so they're different mineral cargo. But also the interrelationships of those different grains tell us that they are growing from a liquid, so a molten liquid. And as part of that liquid solidifying, certain crystals will grow first and other crystals will grow later. But in that crystallization sequence, zircon will precipitate out, so it will drop out. And by dating the zircon, then you have an age of the crystallization of that original liquid.
I mean, what strikes me about geology is how much of a storytelling discipline it is relative to most other things, right? Because it's one thing to just pull out these ages and be like, this rock is this old. But that's not really the place where geology stops, right? Because it has to not just say the age of the rock, but also the provenance and the history and the impact that it's had on everything else. And from what I can tell, I've never been to Australia, but it looks like it's a geologically weird place.
Yeah, so that's exactly right. So it is an analytical science. So you go to the lab and you create these numbers. But what does a number mean? Well, it's really placing that number into some kind of context. So we were talking about those crystals themselves frequently are zoned, and they can have metamorphic overgrowths and cores from somewhere else, as well as an igneous part. So with these beam-based techniques that we use to analyze these crystals, you can get an entire history from a single grain. So you can get a history of the original growth of a rock, the subsequent uplift of that, and then a later metamorphic event. And that's all trapped within one crystal. By doing enough of that work, you can see repeated patterns, and that tends to tell us stories about mountain building events. So as a geologist, we call those orogenies, and that's where two plates tend to collide and they thicken the crust. In thickening the crust, they cause rocks to become melted. And that melting and heating process tends to be recorded either in the new growth of zircon or in overgrowths on the zircon. And if we do that in enough places, we can map out these old mountain belts and see how, then go to the next scale, how these plates collided with each other and broke apart. So, it's not just about the single date, it's about piecing those dates together into some kind of formative history for the planet.
Do you have a favorite geological story?
Of all time?
Of all time, yeah. So one of my friends, she was from South Africa, and she was like, asking people their favorite anything is the most American question that I've ever heard. And for a while, it caused me to stop asking it, but now I've returned to it because I think that it's worthwhile.
I've got lots of cool stories. I think one cool story is about the Musgrave province in Central Australia. So that's quite a trek to get to. So that's along dirt roads for like 3 days, and then probably half a day through no tracks at all. So spectacular scenery, red desert dirt, kangaroos hopping along. But in one part of that province, there's a whole series of volcanoes that are nested on top of each other. So these volcanoes are huge, and they're quite old. They're about 1 billion years old. But the neat thing about that is that each one of these volcanoes is probably equivalent to Yellowstone, and there has been a very large number of them in the same place, just on top of each other in this one place. And if you look at the kind of configuration of the old kind of plates and crotonic parts of Australia, you can see where this is focused is in the junction, the triple point junction between 3 older plates. And it's been the repeated focus of heat over, probably 50 to 100 million years. And the volumes of volcanism are staggering. So in terms of Yellowstones, it's nearly an order of magnitude bigger than Yellowstone.
And then it just stopped?
Yeah, is it asleep?
Then it just stopped. Yeah. Yeah. Thankfully, it just stopped. And that's, as Australia's kind of now configured, it's right in the center, more or less, of that configured plate. So it's nice and stable. But it used to be on the edge of one of the older crotonic blocks. And we infer that's the direction that melts got channeled. So the cool thing about that is, you can build this history up from looking at zircons and dating the zircon, but looking then at other signatures within the zircon helps to tell that story. So looking at the oxygen isotopes within those zircons is important because it tells us where those zircons formed. If those zircons formed in the shallow crust, they would have a different oxygen isotope signature because they will have interacted with meteoric water, so rainwater. As the calderas, these big volcanoes collapsed, they'll have brought down altered rock. And that altered rock melting produces a very distinct isotopic signature, which is different from a mantle signature. So these are quite unusual rocks.
It seems like the oxygen isotopes are also subject to like the different variations in climate too.
Yeah, that's exactly right. So that's why they're a useful marker of where things, in terms, geologists can use them to tell temperatures. But in a zircon context, in this kind of magmatic heterogenesis, we can use it to tell where our melt has come from. Has it come from the mantle? Has it come from reworking older crust? Or has it come from melting altered rock? And this melting altered rock signature is quite unusual. And you find it in places like Iceland, and you find it in this Musgrave province, and it tells us about these supervolcanoes. Interestingly, the oldest rock on the planet, Atacasta, also has a similar signature, this kind of light oxygen isotope signature as well.
Interesting. That's really interesting.
So what that implies is that it's remelting?
It implies it's melting shallow crust that has seen water. So it supports the idea of a wet early planet in Acasta, that is. So if we have a wet early planet with an ocean, and you alter that upper crust, melting that upper crust would produce these sorts of signatures, and that's what's been inferred for the early planet. So everyone thinks the early planet is like being, this kind of hellish, ultra hot, warm body. But I think there's quite a lot of research now that supports it. This is cooler, and it did have oceans pretty early on.
Yeah, that's really interesting change to have seen happen in the last few years, even. So this might make a nice segue, because you are scientifically fixated on the story of the crust and the story of how these continents came to take their shape. And we started talking about that a little bit, but we first found out about you through this, widespread. Let's say fame. Your fame appeared recently, yeah.
Infamy.
Yeah. Infamy, yeah. So you and your colleagues had this really interesting theory which seemed to very intuitively make sense, that things outside of the solar system might be leading to changes on Earth, which is, both terrifying but also fascinating at the same time. And that as the Earth moved through the galaxy, it moves a little bit faster than the galaxy itself rotates. And so it progresses through these spiral arms, and at which point it feels different pressures and different environments that might destabilize its, outer worlds, its nether region. What do we call this?
Oh my goodness.
It's
well,
yeah. That's not right. No. It's
outer
backyard. I don't know. So the solar system's supposed to have this cloud of objects around it, which is responsible for the cometary bombardments and so forth in its early past, deep past, early years. And so perhaps these destabilizations have something to do with the transit of the Earth around the galaxy. And first of all, how did you come up with this idea? But furthermore, how can you tell what's happening on the Earth, and how do you peg it to what's happening in the galaxy? And yeah, just walk us through this.
And one more thing to add to that is, what necessitates such a theory?
Yeah, no. So, wow. Okay. I'll try and unpack that some of that for you. So, how do we start to even get to that scale? We've talked a lot about looking at individual crystals, firing laser and ion beams at them, and calculating an age. And that's the day-to-day job. But if you do that long enough, you create large enough data sets. You plot them against time, and we can look at some chemical variables against time as well. So we get what's known as a time series. So that's time against any sort of measurement. And you do that, and you start noticing kind of patterns in the data, and you start thinking about, well, what can cause these patterns? There's obviously mathematical techniques that we can use to go from that time domain into a frequency domain. So that's like how often something repeats. And we can talk about that as well. But doing that maths really picks out these frequencies. So every roughly 180 to 200 million years, there appears to be a change in crust generation. And we see that in the early history of Earth. So similar sorts of frequencies have actually been pointed out for mass extinctions, for example. But we see this sort of frequency in the deep time record. And by that, I mean time that kind of boggles the mind. So we're looking back probably at over 2 billion years to about 4 billion years. So that's right back into the formative age of our planet. And you go and start to think about, well, what's got a similar 200 million year frequency? And you're spot on. You pointed it out. Well, the transit time for the solar system around the galactic arms, and if you assume 4 galactic arms, the time between each galactic arm is roughly 200 million years. And you then go, how can I cause a crust formation process on Earth by that much larger, grander rhythm? And the most obvious answer to transfer energy into the crust to cause it to melt is through impacting. So the proposal is that the Oort cloud, which is this icy cloud of planetesimals at 2,000 to 100,000 astronomical units from the sun, so right out in the
like far away, like almost a light year or something, like really far away. Yeah,
really far away. Yeah, this cloud maybe gets disturbed and causes these cometary impacts. So whilst Earth has been quite frequently bombarded by near-Earth objects, it's kind of like the background rain out, and it's more difficult to see a frequency in that. So it's easier to impose a frequency on something that's further out because it can be more influenced by galactic tides. Also, the important thing about these cometary impacts from the Oort cloud is they hit with massively more energy. Because of their orbital path, the more energy, the more melting you create.
That's because of their high eccentricity. Is that because they're coming in at such an angle, basically?
Yeah, that's right. And they can be colliding head on as opposed to catching up. So their orbital dynamics help and make them impart a vastly greater amount of energy. More energy means a bigger hole. And a bigger hole means more decompression melting. So basically, if you take a top off a bottle, and that bottle will fizz up, that's pretty much what you do with the Earth, and you cause large volumes of melt, and that's tracked in this isotopic record within the crystals. So I should say it's not just about dating the crystals; it's about dating the crystals and looking at their chemical composition. So we have a time point and also a chemistry point.
And is that part of this harmonics? Is the differences in the chemistry at different ages as well? Can you maybe tell us, because you're correlating two things here together, which is really fascinating. And then you're saying that these frequencies can be explained by this event, basically. What are those two things exactly? One more time. I know you sort of went through it, but what is the actual what were these patterns in and how do those two, the chemistry and the dating, relate to one another? Yeah.
Sure. So we have our uranium lead clock. So that's what we spent a lot of time talking about. And that's the kind of really important piece of information. So that gives us our time variable. The other variable we want is something that tells us about where that melt came from. And we can use a range of isotopes to do that. So we can use oxygen. We've talked about that. And that's one of the things we use. But another isotope that is really useful in zircon is lutetium hafnium. So lutetium hafnium in zircon is cool because zircon doesn't like lutetium, but it loves hafnium. So the signal that I get in my zircon is a signal of the formation. And different parts of Earth and different parts of Earth process have different hafnium signatures. So it's pretty much like me asking someone their surname, someone saying their surname, like let's say Kirkland, and then someone going, oh, well, that's from Scotland or Ireland. It enables you to tell where the crystal has come from. So by looking at these signals, we can see when there's more mantle-derived melt versus more crustally derived melt.
And what kind of differences were you seeing across the ages in these pulses?
Yeah, so it was this cyclical trend between more remelting of crust versus more new melt, where new melt comes from the mantle. So you get these periods where the crust is renewing itself, and then you get these periods where the crust is just reworking itself.
And this was happening with some harmonic regularity.
Yeah, exactly. And it's happening with this roughly 200 million year regularity.
That's really fascinating. And then you start looking for what could have possibly, and then you think to yourself, okay, well, the arm takes about this amount of time. Now, are there other processes besides the transit through the arm that critics have come back and said, oh, well, there's other 200 million year cycles as well that could have, what have you heard anything or?
Yeah. So, and another frequency that is broadly similar, and I say broadly because, these things are like 100 million years to 200 million years. It's roughly the length of time it takes for an ocean to become dense enough to sink. So that's the subduction cycle.
An ocean to sink.
Like the oceanic crust?
Oh, the crust.
Yes, oceanic crust to sink.
We're geology. We don't do water here.
No, we don't do water here. This is rock. This is hardcore.
I've heard of sinking in an ocean, but I've never heard of an ocean sinking itself.
No.
Okay.
Yeah.
I see.
Yeah, so oceanic crust. To become dense enough to sink. So, the mid-ocean ridge, it splits, it goes away, it rifts, and then it cools down. As it cools down, it becomes more dense, and then it starts to subduct. Now, the problem with that is I mentioned the data set that we're looking at is from 2 billion years to 4 billion years. Subduction isn't really very few geologists would have this very early subduction on Earth because early Earth was much warmer. It had much more vigorous convection, and that forms of process were very much vertical mixing rather than horizontal mixing. So that kind of is challenging, and also it's challenging because you would predict that frequency to not remain the same, right? As the planet is cooling down, you would expect that frequency to lengthen, and there's the frequency stays the same.
Is that this explanation that was given to you when you were first starting out training as a scientist, or was that something that struck you as having inconsistencies that needed to be addressed in the future? Just getting back to Anastasia's question at the beginning, like why the necessity for this theory right now? Why were the old explanations for these pulsations, or were these pulsations unknown?
Pulses are unknown. Yeah. I mean, in the more recent Earth pulses, there's a whole range of different processes have been recognized, and there's been a whole range of different explanations. But getting back into early Earth history, our understanding of that, while it is improving, there is much bigger knowledge gaps. The idea of subduction causing this frequency is challenging on the early Earth because very few people think there's subduction. The chemistry of the rocks also don't even support subduction because the style of melting you invoke by taking something from the surface and taking it down deep imparts a quite specific chemistry on rocks, and we don't even see that in the rocks. So there's lots of reasons why subduction doesn't really tick all the boxes. It's a challenging question, right? Because geologists are very focused on explaining processes using internal mechanisms to the planet. And that's because that's stuff you can go and actually measure. And it's also because it's within your discipline. So when you start proposing extraterrestrial processes affecting geology on the planet, you get quite a bit of pushback.
I was just going to say, it's one thing that's just been absolutely, I guess it never has stopped blowing my mind. But when I read the history of science and I read about these people who, some of the foundational people for all of these disciplines, it's like not like they were just a geologist, like they were a physician and a lawyer, and they studied, light and electricity.
And they were also a painter. And
yeah, it's like unbelievable how like wide ranging all of these people were. And I wonder if our system like today, where you spend 16 hours like in one laboratory doing this one little thing, isn't counterproductive in some sense because there's no time to really think about the bigger picture. And for better or for worse, I mean, obviously these methods, these technological methods that we're so fixated on in the university are really productive, right? We can do incredible stuff.
Industrially,
especially industrially. But we also don't have like the same, I mean, it's amazing that you guys were able to publish this paper, I guess, being geologists and then talking about astrophysical processes and not
they
getting...
had somebody from NASA.
Right. Well, I'm sure that's and of course
That
that's
probably
how it's
helps.
done, right? That's how you do it, I suppose. You make friends with somebody at NASA who likes your idea.
So that guy, he was actually a student of ours at Curtin and specialized in dating impacts. So we got other cool stories about dating impacts, but that paper in particular, we got very lucky that we had a very supportive editor who realized that it was going to be provocative, and that in peer review that was never going to be a definitive. All 4 reviewers are not all going to say they love this, and that's okay. I mean, part of the role of I think science is to have things tested by the community.
It should be skeptical. I mean, otherwise it's just a big church or something. Yeah.
Like something that we've really come across in all of our time talking to people, especially these emeritus professors who have started publishing on kind of wilder ideas, is just the fact that as long as you do your homework and you dot your I's and you cross your T's, you can probably find a way to create enough of a coalition to publish even on crazy ideas. Because all ideas are crazy at some point in science. Like anything that changes the paradigm is going to be insane for a good few decades until people finally start to come around. And so it's really good to see stuff like this because it feels like we talk to a lot of people who are very down on the idea of peer review. And that it's very stifling and it prevents big ideas from gaining traction. And I think that is true to a pretty significant degree. But stuff like this is just very exciting on a philosophical level. And my relationship to science as just this larger discipline, I'm like, this is cool. I like this.
Yeah, and I think that it's also extremely responsible how you guys have been like, look, this can't be explained using the extant knowledge about the way these processes have gone down in the past. And so, this opens the door to supplying a new mechanism that makes more sense, perhaps. And it's also really admirable. I noticed in all of the press releases for this, like the last line of them was something like, we're basically just trying to urge geologists to consider that there might be other stuff happening.
That's spot on, because this might not be correct. What I do know is correct is the fundamental data set. So the fundamental, me going in the lab, measuring the uranium lead in those little crystals to get the age, that is correct. And that is new data. So people can interpret that in a variety of different ways. We've presented one interpretation that we believe is consistent or most consistent with that volume of data. But, that is a hypothesis that can be tested and it has its own predictive consequences. One of those consequences would be we would predict, like on the lunar surface, to see a similar sort of periodicity in its cratering record. So that would be something to test this. So I think as scientists, that's our kind of responsibility. Like it's, you take a data set and you interpret it as best you can. It's then up to the scientific community and us as well to go and try and test that. And if it's not an idea that is consistent with its own prediction, then sure, that hypothesis has to be modified and changed, and that's fine. That's science.
And maybe the ideas will come from outside of your wheelhouse, and that's like more important than ever that scientists are able to establish really friendships too, and collaborations with people outside their disciplines. They can, so you can get all these. I honestly wish so badly that like some phase of graduate school would have involved like a deep historic analysis, at least of like your discipline, just to see how these basic ideas came about. It's been, I'm still piecing these things together, even from my own discipline, like the history of how the foundational elements were established in the first place, And
so you're absolutely spot on, because in geology, there has always been this kind of dichotomy between catastrophism, so like events causing big changes, versus uniformitarianism. So what you see today is the processes that you can see through Earth's past. And, for a long time, uniformitarianism has been the way to go, because that's something that seems to accord with the scientific method. In other words, it's something that you can visualize today, is something that you can visualize and consider to have happened in the past. the difficulty of uniformitarianism when you get to early Earth is that early Earth was a very different planet. A large number of processes that we see on the current planet probably didn't happen. And it's pretty much a fact that every part of our planetary surface had been hit by something from outside the planet. I mean, that's how I think most people would be quite happy that our planet solidified and came together in the first place. I like using this response when I get questions about oh, this is just wacky. Yeah, well, I say, like, go out in a nice cloudless night and look up at the moon and look at the craters on that. And just because you can't see as many craters on Earth doesn't mean it didn't suffer as many impacts. In fact, it'll have suffered proportionally more because it's got a much larger gravity well.
It's bigger. Yeah, that's really interesting. Yeah, it's interesting how craters are kind of the go-to explanation for everything when it comes down to like these external interactions with like, has anybody come out and come up with other ideas for how passing through the galactic arm might affect the crust, or might affect orbits? Or have you gotten any of these emails? Or have you had a chance to present this at a conference yet? Have you actually like gone toe to toe with? Not yet. Okay.
We've been pretty much locked down here in Western Australia, so we're only kind of starting to open up now. Yeah, is what it is. It allowed me time to write the paper. So pluses and minuses. But in terms of other processes, there has been other stuff in the literature where you think about having effect on Earth's mantle and causing kind of tides within Earth's mantle because of gravitational interactions. Whether these are plausible or not probably could be nutted out with some calculations.
But they're all essentially gravitational, so they have to do with the density of the different local star systems at the time.
Yeah. So one thing I would pick up on, so you mentioned that craters are the go-to mechanism of seeing extraterrestrial processes, and that's absolutely right. I mean, it's the most obvious manifestation of it. The thing is that our oldest crater is only about 2 billion years old. So going back and having an older record than that, we are probably left with things called spherical beds, which are when an impact comes in, hits the ground and kicks up a lot of material. That material turns into a melt glass and comes down as these fine little vaporized beads. So those beads then form certain parts of the stratigraphy. So that was the neat thing in our work, at least the model for the spiral arm passage. It was spot on with some. Well, it was very close to some spherical beds as well. So we thought that's kind of neat and an extra piece of information.
Do you guys see this moon forming event? This Theia impact business?
So that's kind of
deep.
That's deep. Yeah, that's basically before most of the. Well, it's prior to any real record of the planet, right? Because that Theia collision basically vaporized the majority of the planet, and then it resolidified. What I would say is really interesting is that lots of these different isotope systems. You can remember I was telling you about hafnium, for example, and that tells if stuff comes from the mantle or stuff comes from the crust. You can kind of recast that information back to a prediction of when the material came out of the mantle. And you do that, you can do it for hafnium, you can do it for neodymium. That's a different isotope system. But they seem to point back to about 3.8 everywhere. With two exceptions, one exception being Jack Hills and the other exception being Acasta. And this is kind of interesting. And what I think is going on is at 3.8 is the end of the late heavy bombardment. So normal crust maybe started to really form at that time by more normal crust production processes. Whereas those two places I mentioned, Acasta and Jack Hills, which seem to have this legacy further back, that might be more a legacy of early large impacts on the planet. And indeed, people have talked about the formation of the rocks at Acasta, that's in Canada. These early rocks in Canada as being formed by impact-related processes.
like serious impact, like planets smashing
giant
together.
impacts.
Yeah.
And so is that
giant
why, because in the paper I noticed that your dates start at 3.8 billion years ago.
Mm-hmm.
And so is that why?
Yeah, because it's really difficult to get back past 3.8. There's very few places on the planet that allow you to get back older than 3.8. 3.8 seems to be this cutoff, and people have inferred that's because that's when the late heavy bombardment stopped. So heavy bombardment basically when all these cometary impacts started to slow down. So the planet was getting resurfaced by those impacts. Yeah.
So the moon is about a quarter of the size of Earth. And if the moon is formed partially through an impact of the moon with the Earth, wouldn't that remelt the crust? Like, I mean, it's hard for me to imagine an object a quarter the size of the Earth crashing into us.
Yeah, I think you said it completely resurfaced everything.
And the late heavy bombardment would also make sense to have come from, because I mean, as far as I understand, the model for the late heavy bombardment is the fact that they were coming from elsewhere and arriving here. But again, you have two objects that are on the same order of size crashing into each other. Wouldn't that just kick up a lot of rocks that are then crashing into those objects as they stabilize? Like, is there any sense that the...
Yeah, I think that's right. So like basically you have the Theia collision, which formed our planet essentially. So that's nearly time zero if you want. There is a prehistory prior to that, obviously, but Theia collision forms our moon, forms Earth, then you're raining out this the debris for that and solidifying the planet. So you have that rain out, but you also have other near Earth objects colliding as well. And there's obviously a flux in meteorite impacts, which has decreased through time. But that late heavy bombardment is envisaged to have kind of slowed down at about 3.8. And it's really curious that that's when quite a lot of these isotope schemes, that's as far back as they seem to point. And a reasonable way of interpreting that is that's when the resurfacing of the planet from meteoritic impacts started to slow down. We're not saying that's, it hasn't happened since. It's just that's when the rate started to tail off.
Yeah, and that kind of makes sense with what you're always driving at, which is the fact that if you have like a total melting event 4.5 billion years ago, you would reset all the clocks.
Well, this one was only 3.8, yeah. And then there may have been one before that even, and so on and so forth.
Yeah.
Yeah, so it's like, it's a case of like, okay, this is a very conservative way of putting what we have, because science, is obviously an evidence-based storytelling. And if you don't have evidence from something, like it might be a cool story, but it's very difficult to put it into the pantheon of legends or whatever it is. It doesn't make the scientific cut, basically.
Like if you're gonna shift legends about the formation of the solar system, you kind of have to shift a lot of legends all at once. And so I think it's a zeitgeist thing. Like every single discipline has to suddenly just be like, and go, and then it just shifts to the next ratchet.
Right. That's why it'll be so fascinating to see how the ages of these interstellar meteors turn out. I really hope that you get connected with Avi about this. I'm just...
Yeah. You flicked me an email, so that would be really exciting. I guess the critical thing is like actually getting your hands on a physical piece of something.
It's true. Yeah, that's true.
Yeah, they got to dive deep for those things. I mean, they're going out they're going to go drag the bottom of the ocean somehow, and hopefully something will come of it.
Fingers crossed.
Yeah.
Before we let you go, I have one question, which now that I have a geologist on the phone, I need to answer to my satisfaction. I've read in a lot of papers about the Archean greenstones and that they're really anomalous. And I've kind of the summaries of why they're anomalous tend to get really technical really fast.
Archean greenstone sounds like something out of Lord of the Rings or something.
It really does. I think that it's probably a more boring story than it sounds like, but I have never really quite been able to explain to myself what is weird about them and why people care and why it's important.
Okay, so I'll start and describe Archean greenstones first in a little bit, and then I'll tell you why you care. Archean greenstones are basically, they're kind of green iron and magnesium rich rocks. So we call them mafic. They tend to be, kind of more basaltic in composition. And they're supposed to be this early kind of proto-oceans on the oceanic crust. I got to make sure right. Oceanic crust on the early planet. And their chemistry is kind of quite primitive. So by primitive, I mean quite close to what we might expect mantle compositions to be. So there's some of the earliest, or at least chemically earliest history of the planet, and they surround crustal fragments. So those cratonic fragments are the bits of scum, if you like, that float, and they're the lighter colored rocks, they're the granites. So these greenstones are the primordial oceanic crust, if you like, and they drip down, they fall very vertically around the granite domes, and the granite domes are inferred to have formed from partial melting of those greenstones. So why is that important? Well, the continental crust we live on may have been formed from melting in part those greenstones, and that's the important thing about melting. When you melt something, you don't melt it all. You melt the bits that want to melt first, and they go off, and then the refractory bits, or the bits that don't want to melt, sink, and that creates this vertical kind of circulation. And that's very different from the more modern Earth, which is this horizontal style of plate tectonics. And the reason you're interested is greenstones tend to have lots of gold in them.
I see. Okay.
Right.
Like everything else on it.
Lots of gold.
It all comes down to the gold.
Interesting.
Yeah. So that's where you go and look for gold. So that's the other cool thing. Our planet seems to have metallogenic epochs, so periods of time when more metal were formed. And
what's up with those periods?
Personally, I think that it's ancient civilizations being subducted into the crust and leaving behind their like molten
their
chunks.
Massive computer networks.
Yeah,
they're goodies. Yeah.
It's like subducted trash heaps.
Yeah, we always are trying to imagine, what our civilization would leave behind in the rock record, a million years from now, and probably be some interesting metal veins, and I don't think
maybe some isotopic anomalies, hopefully.
Hopefully. For better or for worse, yeah. It depends who you talk to.
Yeah. So you were asking, why is there specific epochs that have got more metals in them, and it's because fluids were more mobile. So there's only one way really that you can move metals in the crust, and it's with a fluid. That fluid can either be a magma fluid, so a silicate-based fluid, or a hydrothermal, a water-based fluid. So events that cause fluids to move metals around. So a great way of causing metals to move is to have an orogenic event, collide plates into each other, heat up bodies of crust, and create these big hydrothermal circulation cells, and that will move metal about.
So these are always concentrated around mountains?
Certain types of deposits are concentrated around mountains. Other types of deposits are concentrated around rifting. So as you pull plates apart, you're going to have more mantle material coming up. So a good example of that is nickel. And the reason this then is important is if we know where these old rift zones are, you could go and peg some ground and make loads of money by saying, I'm going to go and explore in this area and sell a mining lease over the top of those old rift areas. Whereas if you wanted to go and find gold, you might go, well, I'm looking for mountain belt gold, orogenic gold, and you might have a mapped out old mountain belt, and those would be the areas to go and stake your gold claim on.
So are you planning on leaving academia to start like a mining landlord business, or is that or is that just like a fallback career option?
No, that's a fallback career. It's when it all goes wrong and no one believes me anymore.
Yeah, when you end up on the crackpot index, we'll do our best to keep you off of it. Okay, so then final and last question. Do you have others?
No, go ahead.
Ringwoodite. There is a few.
That's been in the news a bunch.
That's been in the news a bunch. I think the majority of the papers that I found were from maybe like 10 years ago.
Huh.
Yeah.
I wonder why it's popping up.
Maybe there's a new paper.
Yeah, I don't know.
But maybe there is a new paper. But
there's a lot of water down there.
There's a lot of water. And if there is a massive impact event at the time of this transit, do you think that the forecasts that there's, several oceans worth of water in the mantle, could that have liberated sufficient water in order to have created this water world? Because you said that there's a lot of evidence. I think you said that it was an Anacostia, that it's like the upper crust melted and then it was submerged. Do you think that they could be related somehow, or totally different?
Yeah, so the water content is really important, but water content is important because it promotes melting. So it's a volatile. So the more water we have, the easier it is to melt a rock. So if we don't have water, it's actually quite challenging to get, well, you have got to impart more energy to get rocks to melt, which makes it harder to form crust. Now, the thing is with water, we're not talking about, like a big lake in the mantle. What we're talking about is structurally bound water. So that's water bound to the crystal itself. And it requires energy to kind of liberate that water. And that water promotes other chemical reactions, just like a catalyst. And remember, we were talking about those greenstones dripping down, and those greenstones dripping down and then melting and forming crust, and the buoyant crust rising. A really key part of that process is the ability to have water. Otherwise, it becomes very difficult to get those greenstones to melt. And a question that you then get to is, where does that water come from? So originally, people would have said, oh, those greenstones, right, they're at the surface. They will have brought down meteoric water or fluids from Earth's surface to cause the melting. But this is where mantle water, such as in Ringwoodite and other crystal structures like that, comes in and is really important, because if the planet had quite a lot of water already in the mantle, that makes it a much easier process to melt. And then you start to think about, where did the water come from in the first place? Yeah, the traditional view was that, it was delivered by, icy comets delivering water to Earth. But hey, if there's already a lot of water structurally bound in the mantle, maybe we didn't need this rain of, ice balls to Earth. So it's quite important stuff about understanding our early planet. Yeah.
And exactly. And understanding the process of planet formation in general too, because it seems like I'm always looking for the role of water in the universe in general. Like, I did my PhD in a weird form of water chemistry, where we're looking at actually just strange structures that water forms under pressure and under tension and so forth. And it's just such a amazing molecule. Like, it's hard to even overstate just how bizarre water is.
We don't talk about water here, though, because it's geology.
Oh yeah, this is a geology show. Sorry.
You can talk about structurally bound water. That's fine. You can talk about water.
Okay.
Up in crystals. That's fine.
Yeah, it will just be so fascinating to understand how these processes feed back into our understanding of planetary formation, solar system formation, and so forth. We had a guy on the show talking about planetary formation and talking about the giant molecular clouds, that are said to collapse and condense, and he mentioned that those, we're like, well, what are those made out of? And he's like, well, mostly hydrogen and helium. We're like, okay, but then you go and look, and there's hundreds of different complex molecules in these clouds, and the chemistry that could lead, we need to just start exploring this, but the chemistry that could lead to those reactions, and then the geology, and there's so many processes that are intricate to forming this wildly complex system. Even it seems like even in early Earth, just this wild onion layer of a ball that's so much more complex than just a hunk of rock that we normally think of it.
But don't you think it's kind of beautiful, because what you've just described about GCMs, where GCMs condense to form stars, right, or it's right on these galactic arms, which we're also proposing has other effects, right, on our planetary surface as well. So there's this kind of like link from, the smallest grain scale that we've been talking about right through to the galactic scale and back again. So yeah, it's kind of, I think it's great.
And they can each teach each other so much. That's why, again, like, I hope that the worlds of communication do continue to open up like you guys have done. Man, it's been really cool to talk to you. I hope that we can give you a call when we think of more geological questions. It never hurts to have more geologist friends out there to help us interpret the cosmos. Yeah.
And for when we look for gold.
Yeah.
I'm always preoccupied. We live in an area where there's a lot of gold mining, and you walk down to the river and there's just these, there's two dudes, they've showed up with a truck full of boxes and they're going to do some mining on the weekend. And so I'm always like,
sure.
Yeah, maybe we're in the wrong profession.
Get yourself a gold pan. Seriously, get yourself a gold pan and see what you find, because it's really interesting. So just with a gold pan, you might get flecks of gold if you're lucky, but that's only part of the story, because the heavy minerals that you'll separate in your gold plan might tell quite an interesting story about the history of your local area.
How much does it cost to ship rocks to Australia, I wonder? Just like a single bag of rocks.
Only one way to find out.
Yeah, we'll get on it.
Cool.
No, it's been really good, and so thank you for all of your answers and all of your ideas.
And entertaining our crazy questions too. Yeah.
No, it's been cool. It's been really nice talking to you guys. Thanks for your interest.
Where can people find you if they're interested in your work?
Oh yeah, so
Not like physically, not like where are you at right there. GPS coordinates, please.
Curtin University, and if you type in timescales of mineral systems group, you'll find our website, and we've got some kind of popular science conversation pieces about some of the stuff we've dated. So yeah, lots of, well, I think they're fun stories to tell. But, yeah.
Cool, man.
Very cool.
Well,
Thank
have
you.
a great rest of your day. It's just morning there, right?
Thank you. Yeah, it's getting nice and sunny. It's a nice day outside, and I gotta go and see some grad students.
Yeah. All right. Well, don't give them. Don't be too hard on them.
No, I'm not gonna give them any tweezers.
All right. Well, thank you so much.
Take care.
Thank you. Bye, guys.
Bye.